Alright, so, you ready? Are you ready? I know you're ready. You're always ready. Tater tot, you ready? Okay, hurry up, hurry up. So, no talking food. Okay? So finish up first. You ready? Okay, class.
Yes.
Thank you. Alright, good. So, we're gonna go over this, and this one right here has to do with the derivative. So looking at graphs of the derivative, the second derivative, and the function itself, and how they are tying together. So this is a graph explaining what this is. So just by this graph alone, you should be able to identify a lot of these things. So we know when the derivative is equal to 0. I'm right here, right? I know that's going to be min, max, one of those, right? So it's going to be something important when the derivative is equal to 0. Now, when we check our intervals, I check our intervals. So if my derivative is greater than 0, so that means my slope is greater than 0, and then it goes to 0, and then on the other side it goes, the derivative is less than 0, so I have a positive slope up to 0, and on the other side I have a negative slope. So what's it look like I got there? I got a maximum. So it's going up to a maximum if it does that. So we could actually use the first derivative to find out if it's going to be a maximum or a minimum. So it would be a minimum if I go from a negative slope to 0, then over to a positive slope right there. So this graph, hopefully it's going to be, really helpful for you. So right here, absolute max, okay, the prime is undefined, so that is, I cannot take a derivative at that pointy point. So that piece right there, it is not differentiable because there is no slope at the peak of a point. So yes, it's a stabby point, but that does not mean that you could take a derivative there. So the derivative is going to be undefined because of that. And then over here, we have this one right here. It is going to go to a 0, but then this side, it is less than, so that means it's a negative slope, and then it's a 0, then it's a negative slope again. So when you see a negative, negative, and a 0 in between, this is what it's going to look like. Just like over here, on the far side over here, I have greater than 0, so it's going up, goes to 0, and goes up again. So just by using the first derivative test, you should be able to find out or be able to graph what your function should look like because of that. Should, using this right here. So you could use your notes on your test, so hopefully you guys will be like, oh yeah, I could use that. So here it is, local test for extrema. So the following test applies to a continuous function. So it's going to be continuous. So at a critical point C, the derivative changes sign from positive to negative. Okay, that's important. Positive to negative at C, that means that is a greater than 0 for x less than C, and then is less than 0 for x greater than C, then has a local maximum at that point. So again, this is what this is. So it goes to 0. So I have a positive slope, goes to 0, and a negative slope. That means it is going to be some type of max. Does that make sense, or is that nonsense? Denny, are you following there? Okay, so when we do a number line, okay, we'll do a number line. Let's say I get a derivative. It is at 3. My f prime is equal to 0. So because of that, that means that my slope is going to be, remember the derivative is always a slope, right? The derivative is going to be the slope, and so it's going to be 0. So that means that's going to be either a min or a max, depending on what's on the left and right hand side. So in this case right here, it is, the left side of it is positive, So that means that when I plug in numbers on this side, my derivative would be positive. Okay, so let's say f prime of 2 is 1. So it's a positive 1, so that means there's a positive slope, right? So because of that, that would mean that my graph is going to look something like this. It's going to come up to this point. And then on the right-hand side, let's say f prime of 4 is equal to negative 1. That means the slope on the other side of this is going down. Does that make better sense? Okay, so yeah, so that's why we get, if it is a positive then negative, it's a max. Okay, here's another example. It is a positive and a negative, it's a max. But this is an example of where it is undefined. The derivative is going to be undefined because it is a pointy point. Yes, we cannot find the slope at a pointy point. Make sense or no?
Yeah.
Okay. Here's another one. Change the sides. Again, I get my 0. My 0 is going to be right here. Okay, my slope is 0 right there. So if I'm looking at just slopes, that means that this is going to be a negative slope going here. So if it's a negative slope, then changes to a positive slope, that means it's going to be a minimum. Same thing goes for here. This one right here, the pointy point is undefined. I have a negative slope and then a positive slope, so therefore it's going, I should have a local minimum also. Hopefully that's helpful. You got the notes? Okay. Okay, if it does not change signs on both sides, then it has no local extrema at all. Here's one, so if you notice right here, it's a 0, so this is a positive and a positive. So if it doesn't change signs, it's not an extrema. Same thing here, this is another undefined point, but it's a negative and a negative. No extreme. Okay, at left endpoint. So for if my f prime is less than 0, and f prime is greater than 0 for x greater than a, then f has a local maximum or minimum at value a. So what that means is I'm plugging in the endpoints and seeing if it is greater than all the rest. Okay, I'm plugging in the endpoints. Okay, plugging in the endpoints. Okay, so right here, if this is less than this, it is a minimum. If this is more than this over here, then this is a maximum. Again, you could use these charts on the test, so if you need help with this. Same thing goes for right endpoint. So if this is less than all this over here, that is going to be min. If this is more than, it's going to be a max. So we always check our endpoints. So when we actually are doing those, our local mins, local maxes, we find our derivatives equal to 0, and then we plug in that in the endpoints. That's going to tell me min, max, or local, or absolute, global.
If f prime is less than 0, is increasing?
Right, okay, so right here, f prime less than 0 for this first one here. So, see this? Okay, so where this is going to be here at B, so all this right here is less than 0. So that is a slope going down, right? A negative slope to this point right here. And it's an endpoint, so therefore that would be a local min. Over here, if this is going up to an endpoint, that is going to be a local max. All right. Use a first derivative test to find the local extreme values, identify any absolute extrema. All right, we're going to take the first derivative. So f prime of x is going to give me
3x squared
x squared
minus 27.
minus 27, right? Okay, so from here, I need to find where is my derivative equal to 0. That's the first thing I do, okay? Find where my derivative is equal to 0, and that's where I could actually plug in my points in between. So, derivative equal to 0. So factor of 3, and I'm left with x squared minus 9. And what can I do with that 3? Can I divide both sides by 3?
Yeah.
Yeah, so that 3 is going to go away. But x squared minus 9, can I factor that one real quick?
Could you?
Nope.
No. Wait, what do you mean by factor?
Factor. X squared minus 9.
Difference of square.
Difference of squares, that's what we're looking for. Difference of squares. So if we're looking at that, you have an x squared, that's always happy place
X
right there.
plus
Yeah.
3, X minus 9.
Yeah, so we're going to get a 0 equals x plus 3, x minus 3. And when I set each one equal to 0 using zero product rule, if I plug in negative 3 to this first one,
0.
the whole thing would be 0. So I could say that x equals negative 3. If I plug in positive 3 to the second one, I'm going to get the whole thing is going to equal 0 again, right? Because this becomes 0, and anything times 0 is 0. So I get x equals positive 3. Negative 3, positive 3. Okay, now let's go ahead and plug in some numbers to my derivative. If my derivative was, let me see, it was f prime of x equals 3, quantity x squared minus 9. This is going to be a little bit easier to do. I'm going to use the factoring method. You totally just timed out right there. Anyway, so we're going to pick numbers in between to see what happens. So if I pick negative 4, negative 4 squared, 16 minus 9, positive 7. Okay, positive 7 times 3,
21.
positive 21, right? So I know that here, I'm going to have f prime of, let's say, negative 4 is positive 27.
Okay.
Or,
21.
wait, 21, sorry. Did I say 27? I did, sorry. So that's positive. So what do I know about this? So on a graph, it's going up right here. Can't believe that. So I know my graph is going up right here. Okay, so my graph is going to look like it's going up. So I know it goes to a 0, and I just need to see what happens after that. So after negative 3, so let's plug in negative 3, negative 2. Negative 2 squared,
4,
4 minus 9,
5.
negative 5.
Yeah.
Negative 5 times 3, negative 15. So the slope is negative. So that means it's changing, and it's going negative here, right? So it's going down to something over here. Okay? And so if I check the other side, so let's do 4. So f prime of 4, 4 squared is 16, minus 9 is 7, 7 times 3 is 21. So that's a positive number. So that means that it goes to a slope of 0 right here, and then all of a sudden it changes up to a positive slope. And so this is going to just keep going on up this way, and this is just kind of exaggerated because my function is a third degree, so therefore, if it was a second degree, that would just be a parabola, right?
Yeah.
A second degree would be a parabola. A third degree is the wacky wavy inflatable R-man, right? So one up, one down. Yeah, so it's one up, one down. So that's what the graph is going to look like using my first derivative test. So I tested the slope over here. So I know it's going to be increasing. So I'm going to have a increasing slope from negative infinity to 3, right? So from negative infinity to 3, it's increasing. And is it increasing anywhere else? Yes, it is.
Increasing.
From 3 to infinity.
Oh,
Because I have more than one place that it's going up, right? That's my increasing. And then decreasing. Decreasing is going to be from negative 3. Sorry, that's a negative 3 right there. Negative 3 to positive 3. Like that. Yes, no, maybe? Possibly. On occasion. Yes?
yeah.
Okay. All right, concavity. The graph of a differentiable function y is equal to f of x is concave up on an open interval if y prime is increasing on the interval. Concave down. So, you ready to throw up some gang size here? You ready? Gotta throw up some concave up, right?
No.
Yeah, gotta get the concave up. Yeah, got those. So, think about it. If it was a concave up, what do you think that is right there in the saddle right there?
The 0 or minimum.
Yeah, it's a minimum, right? So if you think about it, so right here, if it's concave up, it is, okay, that's going to be a minimum, and I'm going to have a 0 right there. And then, let's throw up the other gate side, concave down. So that means that right there, in the saddle of that would be, okay, a maximum. That's important to understand. So as you're throwing up those signs, okay, it is beneficial, it is helpful, right? Gotta throw up that. Anyway, all right, so here's an example of it. So right here, where y prime decreases, so what that means is it is decreasing. So it is increasing, right? So it's still going up, isn't it? But these are all negative slopes, okay? So right here, it is decreasing. So it's still increasing at a decreasing rate. So if I look at the slope down here, like way down here, it's a lot higher, right? Than what I get way over here. So my slope is still increasing here, but it's lessening. It's at a decreasing rate. That makes sense or no? It's increasing, it's all going up, okay? But because it's going lower and lower and lower, it's at a decreasing rate.
So like acceleration.
Yeah, we're actually going to get to that. We're going to do second derivative here in a moment. So right here, on the right-hand side, it starts off here, right? So the slope is going up, but isn't this at an increasing rate?
Yes.
Yeah, it's getting steeper and steeper and steeper. Yes? So it's increasing at an increasing rate.
It's just an additional line it's just getting with me.
My red ones or theirs?
The red ones.
Mine or
No,
theirs?
no. Those extra like lines that it's making it look like a rib cage.
Yeah, they put them all in there to show like the slopes in between different points, but the graph's not very good on that.
Yeah.
They should have just found points like way off to the side, like not on top of each other.
Okay.
Okay. All right, the graph of a twice differentiable function, concave up open interval, y double prime is greater than 0. So it's going to be concave up. All right, throw those gang signs. Okay, I'll throw the gang sign. Yes. So right here, so it's going to be concave up. We just threw the gang sign for that. Okay, it's where my y double prime is greater than 0. Concave down, throw the other gang sign. Okay, open interval where y double prime is less than 0. And now the point of inflection, since we have got to throw up both gang signs. You ready? Throw up both gang signs right now. Bam. Now, you know where your fingers come together right there, where it's changing from a concave up to a concave down? That is your inflection point. That is changing concavity. So right there, that is going to be when your second derivative equals 0. So this right here is where your y double prime is equal to 0. Your point of inflection is your y double prime equals 0. It's not on the notes, but you guys are writing it in the notes, right? Y double prime is equal to 0. Use concavity test to determine concavity of this on the interval from 2 to 8. So we got to do the derivative twice, right? Right, Danny? You're not listening to your earbud right now, right? So first derivative is going to be 2x, right?
Yeah.
And second derivative? So, using first derivative, the concavity test, which goes to this one right here, where the second derivative is greater than 0 or less than 0. Now, on this one right here, what is the second derivative?
Constant.
It's a constant. So is that greater than 0 or less than 0? It's always going to be greater than 0, isn't it?
Yeah.
Okay. So if it's greater than 0, what's that tell me? Now, let's go back to what this function is. You already know what this function is.
Parabola, quadratics.
X squared is a
Parabola.
parabola. It's a parabola, right? X squared is a parabola. We already know it's a parabola, right? So we should already know it's already concave up, right? Okay, so because of that, right here, my second derivative says I only have it positive, right? Since I only have it positive, that means all I have is concave up.
Yeah.
There's nowhere in which that it changes.
Yeah.
There's no changing at all. So therefore, it's all positive, so it's all concave up. So this is already proving what we've already known about x squared. X squared is a parabola. Parabola is concave up. And now this shows the math to prove concavity. So, we okay there? Hopefully. And is this the last one? I think there's one more after
One
this.
more slide and I'll
Yeah, okay, so I will leave off here. We'll pick this one up tomorrow. And then I want you to actually finish up the assignment for the last one. And so hopefully the graph for the functions will help you finish up those homeworks.